In the last two videos, I started by talking about how Heisenberg explained his uncertainty principle using the example of trying to use say a microscope to measure the position of an electron accurately, and that the very act of measurement to find the position of an electron, in the very act of measurement, the photon could knock the electron off, and so that it can take any random momentum, right? So that it would increase the uncertainty in the momentum. Now that understanding gives us an idea that gives us the impression that the delta x and the delta p in the measurements are in the uncertainty relation. They are like random errors and errors of measurement. Now, in fact, in the wave picture, in this wave theory of particles, the actual meaning in this wave theory or wave nature of particles is slightly different. Let's make use of these pictures here about the waves, about what I explained in the last video, to try and understand the uncertainty principle a bit more in relation to Heisenberg's example. So in the last video, I talked about how if you add up these waves of different wavelengths, you can get a wave that has a much smaller range of x. Okay, so if each of these waves is infinitely long, right? Infinitely long, each one has a definite wavelength. But when you add them up, you end up with a wave that has more amplitude in a small region of position, and further away, the amplitude gets very small. Okay, so this gives us the idea that the particle is somewhere around here within this narrow range of position. Right, and conversely, we also understand that if you have a wave like this, it must at the same time be made up of all these different wavelengths added together. So all these different wavelengths, they're not gone, they're added together and they're part of this. They're part of this. Okay, a bit like the analogy that Schrödinger's cat is dead and alive at the same time. So it's as if if an electron is within this range, right? If we know that an electron is definitely within this range, it means that that electron must contain all these different wavelengths or momenta at the same time. Right? It's a very in our everyday experience, is a very, very strange situation. Right? And it's like a stone has different velocities at the same time. A stone can be moving at 1 meters per second, 2 meters per second, and 3 meters per second at the same time, a single stone. That's the kind of thing that we're trying to say with this picture here. Right. So coming back to this uncertainty relation, the actual meaning, therefore, is not about random measurement errors. Okay? It's about saying that if an electron is localized, right, is restricted to be within a certain range of position delta x, then the wave nature of the electron must mean that it has to at the same time consist of many momenta of different wavelengths within a range of momentum given by the delta p in this relation. Okay, so that means that all the different momenta are actually there at the same time. They're actually there in the same time. Okay, it doesn't mean that that the electron has just one of these momenta which we don't know about, or which it picked randomly. Okay, they're actually all there at the same time. It's just that if we ever try to measure the momentum of this electron, right, the very act of measuring it would force the electron to fall into, to actually collapse into one of these waves. right, which is the word that is often used to describe this. So, but I think I won't go into that detail. What I'll do is I'll work out an example to illustrate how we use this idea of the uncertainty principle. How we use this idea about that the electron, for example, in a certain range of position must actually be made up of a range of different momentum. And one of the simple examples that are often used and useful to illustrate this point is the size of an atom, and the energy of the electron in the atom. So let me take a look at that. Now, in a past video, I've talked about the atom, the hydrogen atom, okay, where we have a proton, the nucleus, and an electron going around the atom. So, I have went into some details about forces and number of waves and energies and so on and so on. Now, what I'm going to do this time is to do something very, very approximate, right? So quite the opposite of the details that I went into previously. Now, this is what I'm going to do using the uncertainties principle. I'm going to say, right, the radius of an atom, say hydrogen atom, is about 1 angstrom. So we're going to be quite approximate, but reasonably approximate. I'm not going to say 1000 angstrom for the size of the atom, for example. So we have seen that the radius of the smallest orbit in the hydrogen atom is 0.5 something of an angstrom. Okay, so about 1 angstrom would be about right. So now, and the electron, right? The electron is kind of forced to stay around the atom by the attraction from the proton. So there's this restriction. This force that makes the electron stay around here instead of just drifting away. Okay. Now, so if I look at the full length of this, or diameter of this atom, it would be, say, it would have a diameter of, say, 2 angstrom. So let me imagine, say, a line, the x-axis. Let's say that's the origin, and suppose that a particle is in this one dimension, and it is within the range of plus and minus 1 angstrom. Okay, so kind of like the size of an atom, but in 1D instead of 3 dimension. So this means that let's imagine that the electron is somehow forced to stay in this range. Maybe we somehow build some wall around it. Okay, so prevent the electron from going out. So some walls there, so the electrons can go out. So I have this electron, and it can only move around in this what looks like a well. Okay, so it can just move around in here. It's forced to stay in this region. Now, And we're not even going to worry about what it is that forces it to stay. We know that in an atom it is the Coulomb electrical attraction from the proton that attracts the electron and forces it to stay around here. So in this example here, I'm not even going to worry about what it is that causes the electron to stay in this region. I'm just going to say, right, there's something that forces it to stay there somehow. Right? And we know that an example is the Coulomb, the electrical attraction. Right, so we have this information, right? In this example, we have this information that the electron is somehow forced to stay within a range of position of about, say, 2 angstrom wide. And it can't go out, but it can move around freely in here. Okay, so in terms of the uncertainty principle, we can say that delta x is about 2 angstrom. Okay, and then we know that if the delta x is, if the possible range of momentum is 2 angstrom, we can use the uncertainty relation to calculate what is the range of momenta that this electron must have. So let's try that. Now, delta x times delta p is about the Planck's constant, is the uncertainty relation. So if I want the actual range of momenta that this electron must have, remember that we need to think of this delta p as the actual range, the actual momenta that the electron has, and not some error of measurements anymore. Okay, so h over delta x. Now if we calculate this, now h is 6.63 times 10 to the power of minus 34, I think, divided by the delta x, 2 angstrom, that's 2 times 10 to the minus 10 meter. Okay, so that's joule second, that's meter. Okay, so that gives us write down the answer for this. 5.273 times 10 to the power of minus 25 kg meter per second. So that's our range of momenta. Now from this range of momenta, I would like to find the maximum energy that this electron would have. So I would need some detail, a little bit more detail about these numbers. I would calculate the energy using by calculating the maximum kinetic energy, P squared over 2m. Now, but what is the maximum kinetic energy? How can I get it from this momentum range? Right, the way to get that is to look at this picture and say, right, this electron is sort of maybe bouncing around in this, between these two walls. So it is likely to have momenta or velocities in both directions. Okay, so we know that momentum is a vector. So the delta p, this range of momentum, must be the momentum, maybe the maximum momentum in one direction minus the maximum momentum in the other direction. So in the other direction, since we are along just one dimension, I can represent the other direction by minus p. So plus p and minus p. So therefore, I can think that the difference between those two, P and minus P, is the delta P. Okay, so that means I can think that the range of momentum is the maximum in one direction minus the maximum in the other direction. So this is 2P, this is just 2P. And that gives me a way of finding P. So P is just equal to half of this. Okay, P is just equal to half of this. Now, and this value can go into there. And then M will be, I'm talking about the electron. So M is ME, which is, let me write down ME, just to make sure that we know we have the numbers that we need. So ME is 9.1 times 10 to the power minus 1 kilogram. So we know ME, we know P. Okay, therefore we can use this formula now. Now, if I carry out the calculation, I will get the answer in joules. But I would like to express that in EV, so that I can compare easily with the results for the hydrogen atom. So if I express this in EV, my answer would be about 9.4 EV. 9.4 EV. Right. So if we now think about the kind of oh wait, just a moment. This energy here is the kinetic energy. Let me make that quite clear. It's the kinetic energy, not the total energy. Okay, so we are talking about the KE here. Now, if you recall from the examples with the hydrogen atom, for the hydrogen atom, the n equals to 1 orbit. Okay, has an energy of minus 13.6 EV. If you look back at my earlier videos. Now this minus 13.6 EV is actually the total of KE plus PE. But from the kind of calculations I did in the earlier videos, you can see that the actual values of the KE and PE is about the same kind of magnitude. All right, meaning they're all roughly equal to a few, maybe 10 EV or a few EV also. Is that this kind of order of magnitude. So what we have here, therefore, the 9.4 EV obtained from the uncertainty principle is therefore quite close, or maybe not very close, but similar in magnitude to the kind of value that we would obtain with a more accurate calculation or measurement. So this means that using the uncertainty principle, which is just a simple formula, it is possible to make very quick and easy estimates of the kind of range of energy that is present in an atom, for example, or in anything. In fact, as long as we know the size of that thing, like the atom, we can estimate what must be the range of energy of the particle in that object. And we can do that without knowing anything about how that particle moves around, about what kind of forces are involved. And we don't have to know anything about that at all. All we need to know is the size of that atom or object. And we could go through this uncertainty relation and estimate a value for the kinetic energy. So that makes the uncertainty relation something very useful for doing such quick estimates. Okay. And it, in a way, if you look at this, it even provides us with a way, since it can give us a way to calculate a value that is quite close to the actual, that is not so far from the actual value. It also means that what we understand about the uncertainty relation gives us a way to explain why electrons in an atom has energies that are of this kind of value, of a number of electron volts. And the explanation is quite simple. It consists of two parts. One part is that it's because the electrons are restricted to within this region of about 1 or 2 angstrom of space, and the other reason is because the electron has wave property.